Voice of the Sea, learning from experts across the ocean.
Welcome to Voice of the Sea. In this episode of Voice of the Sea,
we're on the Big Island looking at the impact of lava flows on the Kalapana area and how researchers track these flows. We check out some of the gear they use and learn what it's like to do research on the edge of a volcano. We also take a look at some of the equipment used to replicate volcanic reactions inside the laboratory at the University of Hawaii Center for Volcanology on Oahu. We start off on the Big Island, catching up with U.S. Geological Survey team member Matt Patrick and volunteer Tristan McDonald.
So we're standing here high and dry on some very warm lava. What can you tell me about how your studies here affect our understanding of the formation of the Hawaiian Islands, or even our understanding of the Pacific Ocean basin?
Most of the, or much of the ocean floor is what we're standing on, basalt. So in that sense, much of what's underneath the floor of the ocean is a volcanic surface. Actually, it's most of the surface of the Earth.
So can you just give me an overview of the Big Island, starting maybe from Loihe to Mauna Loa and the different volcanic activity areas?
Yeah. Okay. So in the very south and underwater, we have Loihe, which is the youngest Hawaiian volcano, and then traveling north, we have Kilauea, which we're standing on the south flank of. Just north of Kilauea, we have Mauna Loa, and Mauna Loa is massive. It's the largest volcano on Earth, and it occupies about 50% of the Big Island. And then we have Haualai, just to the west, now near Kailua Kona. That last erupted in 1801.
Oh, wow.
Mauna Kea, it last erupted around 3,000 or 4,000 years ago. And then we have Kohala at the very north part of the island, it last erupted 60,000 years ago.
Okay, Matt, so we're about to head out onto these lava fields, and you made me put on these gloves. Why am I wearing these?
Okay, well, if you look down at the surface, you see it's really broken up and it's covered in sharp shards of glass, and it is literally a volcanic glass. So if you were to trip, and you can see how easy it is to trip here with the irregular surface, the instinct is to put your hands out and catch yourself. And of course, when you do that, you're going to be, dragging your hands on glass. And so gloves are one of the most important pieces of safety gear that we wear out on the flow field. The greatest danger out here is basically heat exhaustion, because you can see there's no shade here, obviously.
Right.
So you have the heat from the sun. And then the ground that you're walking on is warm to hot. So you have all of that upwelling heat. And then you usually, if you're mapping next to a flow, you have intense heat from the side. So it's coming from all directions. So we always wear, sun protection and carry lots and lots of water. So, and take frequent breaks so that we don't overexert ourselves.
Is that what you have in the backpack?
Yep.
There?
Mm-hmm. Yeah.
Mostly water?
Yeah. Actually, yeah. We generally bring a lot more water than you would normally bring on a hike.
I want to ask you about the equipment that you're carrying with you. You have a backpack and a GPS unit. Is that what you normally bring out here on the lava?
Yep. One of the most important tools, like I said, is the GPS, and we use this for mapping of the flow. And we come out on here when the flows are threatening. We'll come out on a daily basis and walk the margin of the flow with the GPS to record its position. Once it's started, then it'll show our track as a blue line.
Okay.
So we can just walk along this margin here.
And am I going to walk as close as I can to this newer flow?
Yeah, well, you have to consider that the accuracy of the GPS is at best a few meters. So
I see.
You want to get close, but you don't have to get right on top of it. Generally within a meter or so.
I don't have to worry about melting my shoes.
Well, that's another thing. When it's active, you obviously don't want to step too close to it because, well, first of all, it's uncomfortable because of the heat, and also you don't want to risk tripping and stepping into it. So you want to give it give it some space. So generally a couple meters is good.
Okay. So you would just walk along like this then?
Yep. Mm-hmm.
And so right here, I can see this is the new flow coming down.
Mm-hmm.
And so I'm going to make sort of a left-hand turn.
Yep.
Oh, it does get really curvy.
Yeah, it's a very irregular margin. It's generally not very smooth because you have these individual toes of lava that poke out and burst out the margins. Here it's really easy because we have the vegetation as a guide to show us what's the old lava.
And so even though there's nothing growing right here, this is still the old, and then this more sort of bulbous, and I don't know, to me it looks a little bit like black chewing gum with the bubbles.
Yeah, you can see it has a shinier appearance. It's also a lot more fragmented on the surface. So that gives you a sense that it's newer.
So the new flow is actually surrounding this
this area, yeah.
Oh, right, and I have a circle on the GPS.
So the flows that we're standing on right now are from January of this year.
No way.
Yeah.
It's that recent. Wow.
And you can see that obviously these are so new that they don't have any vegetation that's taken root. Flows came down the east margin of the flow field and crept in this direction to the south and southeast. And we're moving in the direction of these houses, this Kalapana Garden subdivision, which is just to our east.
Were you out here during the time, we're talking only 6 months ago where this lava was flowing?
Absolutely, we were out here every day mapping the flow field, walking, using our GPS unit to basically walk and follow the margin, and then updating that every day, using that map of the flow, that daily map of the flow to measure advance rates and to be able to project where the flow was going to be over the next 24 or 48 hours. The Hawaiian volcanoes, they erupt normally in one of two spots, the caldera or the rift zones. At Kilauea, what's interesting right now is that we have eruptions in both of those locations going on simultaneous.
And where's this lava flow coming from?
This is coming from the East Rift Zone.
And when people are concerned about VOG or the chemicals that are released from the volcano, that's mostly coming from Pu'o'o?
For the most part from Pu'o'o, that was the active vent. But 3 years ago, the summit eruption started. And so now we have two contributors to VOG.
And the chemicals that are coming out of those plumes, it changes over time.
Yeah, and distance. The VOG, it's a mixture of sulfur dioxide and acid particles like H2SO4. When you're at the vent, it's mostly sulfur dioxide, but that sulfur dioxide converts into acid droplets, H2SO4, over distances. So if you were in Kona, that many miles from the vent, you would have more of those acid droplets than you would at the vent. And in the last year, the flows crept once again into Kalapana, and since 1990, people have rebuilt on the flows. So they've rebuilt on the 1990 flows.
The Curriculum Research and Development Group in the College of Education at the University of Hawaii at Manoa. CRDG's training roots go back over 40 years. Through professional development programs, curriculum workshops, research on teaching methodology, individualized school and district training, and so much more. The Curriculum Research and Development Group, improving schools, improving education. CRDG.
Voice of the Sea, learning from experts across the ocean.
And in the last year, the flows crept once again into Kalapana, and since 1990, people have rebuilt on the flows. So they've rebuilt on the 1990 flows. And you can identify the 1990 flows by the flows with vegetation on them. So they've been here long enough for ferns to set in. Like you see over there, there are houses rebuilt on these 1990 flows. So these houses were threatened. So we obviously were on heightened alert, and we're coming down here on a daily basis, mapping the flow margin and measuring its advancement rate. And
Now, I understand it's dangerous for the structure, but is it dangerous for the people that live there? I mean, does it advance fast enough where they might be hurt?
No, the flows, it's mostly a threat to property because the flows travel slowly enough that you could, in most cases, outwalk them. The flow activity can be a threat, though, at where the lava enters the ocean. And in this case, it's often visitors who are venturing too close to the ocean entry. And at the ocean entry, there are a couple hazards. There's the gas plume and the seawater plume, where it's a steam plume, basically, with volcanic particles and gas that's mixed in.
And so why is that there at the ocean and the flow itself isn't giving off the steam?
There is a little bit of gas that the flow gives off on the surface here, but it's generally minimal. Not nearly as much as if you were up near the vent, where the bulk of the gas is coming out. At the ocean entry, there are a number of hazards. There's the steam plume. There's also what's called the bench, and when the lava enters the water, it builds out a bench. It's like a delta. And it looks stable, and so people venture out on top of it and walk all over it. But in actuality, it's built on unconsolidated sediments, so it's prone to collapse. And it's normal for benches to collapse, and so there have been several deaths in the last 28 years associated with that. Another hazard is when these bench collapses occur, it can often trigger explosions that can throw blocks the size of a basketball several hundred yards inland. So even if you're not on the bench, you're on the sea cliff, you can still be in that hazard zone. If we get up here, we'll also be able to see over here one of the destroyed structures. So in the last year, as the lava flows came into Kalapana Gardens, 3 houses were destroyed. These were 3 occupied structures, so they weren't abandoned, they were actually being lived in. And the first house was a house over there closer to the ocean that was destroyed last July. And then in November, the flows crept farther east and they destroyed a house that's now buried in that direction, just to our west. And the final one in January, on January 17th, a house just to our northwest, and you can see the frame. It was a Quonset hut that was destroyed. We can't approach the house because it's still her private property, just because her her property is covered by lava, it's still her property. So it's a pretty stressful period for homeowners here when you have your house, just a stone's throw over there and you're watching the flows come. I mean, I can imagine. But it's, at the same time, I think, many, even though, they have property here and they see the flows threatening, I think a lot of people at the same time accept that this is nature, this is Pele. So.
But as a geologist, I mean, I would imagine that you'd be really excited to get to witness that.
Yeah, being able to work around flows is really a privilege in any setting. So, and to be able to help with the hazard assessment and be able to help the community is also a great privilege. So this is one of the best places on Earth to come and to actually see active lava. But yeah, there's really nothing like it. Once you see an active volcano, it really sticks with you. So it's hard to shake off.
Exploring Our Fluid Earth is a dynamic curriculum developed by the University of Hawaii's Curriculum Research and Development Group, teaching ocean science concepts through the disciplines of physics, chemistry, biology, and ecology. Exploring Our Fluid Earth is now available freely online. Find out more at exploringourfluidearth.org. You're watching Voice of the Sea.
So Tristan, you're a volunteer here at USGS at the Hawaii Volcano Observatory. You don't get paid to do this.
That's correct. Well, not in money.
So what's your motivation?
It's mostly just the experience. It's a once-in-a-lifetime experience. There's really nowhere else on Earth where we can do this kind of scientific work right now. The hotspot activity that we see, like Matt said, there are other hotspots, but this one lends itself to being studied in a way that others really don't. And so I'm hoping that the experience here will help me in my further career in going to graduate school and eventually finding gainful employment.
So you completed your undergraduate degree
correct,
then?
yep.
And what was that in?
Geology. Yeah.
And so you always wanted to be a geologist?
No, I ended up at geology through a number of selection methods. I originally didn't really know what I wanted to do, so I took a bunch of different introductory classes and decided on geology mainly because I get to spend a lot of time outside, and I like the people who also like geology.
So science is not just about the objects that you're studying, but there's a community of scientists?
That's definitely a big part of it for me, is that the people who are involved in the scientific community are people that I like to be around and get involved with. And another great thing about geology is, we're very, it helps you to realize how small and insignificant you are when you learn about the geologic timescale and learn about the magnitude of the processes that go on within our Earth. And just to be a small human and try to understand these vast and enormous things that are going on that we can't, we can only see, a very limited amount of surface area, and from that try to deduce what's going on underground. It's really, and just today we have the technology to begin to be able to really make some interesting observations and learn some very great things about what's going on.
What are some of the more interesting things that you've gotten to do in your time here?
The highlights so far have been going on overflights in the helicopter, going to Pu'u'o, going into the caldera floor, going to places where normally visitors aren't allowed to go. So in that way, it's an extra once in a lifetime opportunity, because normally I wouldn't have access to those areas as just a regular hiker. So that's been one thing. Another thing has been just being able to be exposed to doctors and master's degree scientists who are doing cutting edge science right in front of me, and I can go to that person's office and ask them a question, or go to a presentation that they're giving about the latest breakthrough, and to really be a working part of a state-of-the-art facility has been a great opportunity.
So what are some of the research projects that you've sort of got your hands into?
Matt and I are working on a project where, can I talk about this, Matt? Matt and I are working on a project where we're mapping the fumaroles, or the steam and sulfur gas vents in the caldera floor. And we're comparing that data that we measure by hand. We walk all around the caldera floor and take measurements by hand, and then we compare that with thermal satellite data. And the purpose of that is to develop a baseline of what the normal temperature regime is within that environment, so that if we start seeing some other precursors for an eruption, maybe the tilt or the seismograms or something like that, we can go and take temperature measurements and see if there is anomalous activity, which often has been shown to precede eruptions in other volcanoes.
So when you say you're taking measurements by hand, you're not literally sticking your hand in the lava?
No, we have what's called a thermocouple, which is an electronic temperature measuring device which uses two metals with different resistivities, and it uses the change in resistivity as the temperature changes to measure the temperature.
So how hot are we talking about?
We take measurements from about 40 to about 100 degrees Celsius at the surface of the caldera floor.
And so that is something I could stick a regular thermometer into, and it would give me a fairly accurate reading.
Yeah.
It wouldn't melt it.
No, you would be in greater danger of burning your hand in some spots. There's some spots where it's actually pretty hot.
But the molten magma itself, how hot is that?
That's like Matt said, it's around 1,100 degrees with some variations.
The Hawaiian Volcano Observatory, it's one of the best places on Earth for a volcanologist to work, because there's so much going on. Right now we have 2 eruptions. They're changing every day. There's something new to see really every day, and every day we walk into the office, there's something new and exciting.
So this is like your dream job?
Oh, absolutely, yeah.
Next, Kanisa heads to Oahu to learn how researchers recreate volcanic reactions in the laboratory.
We're here in Julia Hammer's lab, where they study all major aspects of volcanic systems. For example, how magma rises during a volcanic eruption and what type of rock or crystal will be formed when the volcano erupts. The lab has specialized equipment that they use to create volcanic crystals and collect data on the chemical composition and physical properties of those crystals. I caught up with researcher Thomas Shea, who is conducting experiments on the formation of minerals during volcanic eruptions.
Here, I'll have you participate.
Oh, wow.
And,
What do I do?
Just hold this. I'll grab it from you.
His work is really, really hot, up to 1700 degrees Celsius, which is over 3000 degrees Fahrenheit.
And so this is my vessel. You can see it's red hot. It's about 900 degrees.
In the capsule, Thomas creates an environment like an active volcano, with very high temperature and lots of pressure. He simulates natural and synthetic crystal formation from the surface down to 7 miles deep in the Earth's crust.
Here we go. You can consider that what was molten inside my capsule becomes a volcanic rock, or at least a replicate of it, in about 20 seconds. So we try to have it cool as fast as possible. So to replicate something that, for example, is erupted at the surface, goes from 900 or 1000 degrees to surface temperatures, the difference is huge. So if we want to replicate that, we also want to try and do that as quickly as possible.
And the metal alloy that's protecting the capsule, that cools down quickly?
Yeah, fairly quickly. I mean, as soon as you put it in the water, usually the compressed air will only cool it by maybe a couple hundred degrees at most. And as soon as you put it in the water, this is really when we consider our magma is solidified. So what we obtain is a volcanic glass plus its crystals. And we use the term volcanic glass because it has no particular structure. Its molecules are kind of randomly arranged.
And is that because it cooled so fast?
Exactly. So this is the reason why.
It didn't have time to orient itself.
To organize it, the molecules didn't have time to organize themselves into a structured arrangement, which becomes a mineral, in fact. So.
After cooling, the crystals in the capsule can be examined under a standard microscope or with an electron beam microscope to look at more detail. Samantha Jacob shows us what the experimental crystals look like after they've been polished and sliced very thin. With the powerful scanning electron microscope, she is able to see the crystal structure and determine what they're made of and how they formed. All of this work helps researchers better understand what is happening to the Earth's crust as volcanoes erupt, and it helps them predict what will happen when volcanic magma collides with the land and with ocean water.